This is the 4-1 notes for Calculus 1. The previous chapter, the main focus was on learning how to find derivatives for various types of functions, as well as rules that you apply in certain scenarios for finding derivatives. There were a couple applications, but chapter 4 its sole purpose is to learn about the key applications of derivatives in calculus. Our first stop is the concept of maxima and minima. That will be basically the max and min values along a graph. We start with a definition of the term absolute maximum and minimum. There will be another type of maximum minimum soon, but for now we start with absolute. The definition is kind of hard to read, but basically what it's saying is that suppose you have a function f on some interval, we'll call I, containing a point C. So if all of the y value for that point C is bigger than all the y values on that interval, then we know that it's going to be considered an absolute maximum on the graph. Well, that makes sense. So basically, an absolute maximum refers to the highest value of y that the graph will take, and therefore the highest value up on the graph. So same thing, but in the opposite direction. If you have some value of c and its function value of y is smaller than any of the other function values on the interval, then it's called an absolute minimum. So literally, all you're looking for on a graph is the tallest value, or the value below on the graph that's the most low on the graph. So let's just look at a really quick example. So let's say over here, this is your function. Looks polynomial in nature, but you can see that it's limited to only the interval a to b. So we're going to say, let's just say a to b, or a to d, I apologize, a to d. It says, for example, what values of x are the absolute extrema located on to the right? So we use the term extrema to represent all maximums and minimums. It's just a fancy word to describe all of them in one bucket, so to speak. So if I want to find absolute extrema, they're saying find the absolute minimum and maximum. You can identify these by their value of x. So on this graph, we would look for the highest value of y, the largest value of y across the entire graph, or the highest point on the graph, and clearly that is occurring right here at x equals a. So the absolute maximum would be at x equals a. What about the minimum? It appears if you follow the entire graph all the way down, it appears that the absolute minimum is occurring here at x is equal to d. So we're basically looking in a scenario where we have an absolute max and min on, it looks like the endpoints of the interval, which is not always the case for sure, and you'll see a lot of examples in the section that will kind of show that, but just remember when you're identifying that, you only go from the interval in which they actually tell you to. Okay, so in calculus, we're not only interested in just the absolute maximum minimum, we also have another concept called the local maximum minimum. So the difference between what they are is basically this. A local maximum and min is the highest point in the vicinity of the graph. So for example, if you look at our original graph here, the one we've been using, if you look on the spectrum, if you look at x equals b, for example, you have a point here that happens to be the lowest point in the vicinity of what's going on in this graph right here. Lowest point in the vicinity. Therefore, we would call that a local minimum. So you can see here the value x equals b is called a local minimum because it's the lowest value among the nearby points. Similarly, if you go over to c, if you look here at this guy, if you look around, it looks like it is the highest point in the vicinity, so therefore this is called a local maximum at x is equal to c. Okay, so there is some, and there's a definition here that kind of points that out in a similar manner to the absolutes, but there is something that's extremely important about what's going on in this graph. So I'm just going to get rid of some of the extra stuff here. Whenever you are deciding between absolute and local mins and maxes, you must understand that local minimums and maxes can only occur at interior points. So that means they cannot occur at the endpoints of the spectrum. So if you go to A and say, hey, that's a local max, that is incorrect. It is not a local max because it is an endpoint of the graph. And why is that? Because we don't know where this goes. We don't know if it goes that way or this way. We have no idea. So we can't make a judgment about the vicinity at an endpoint. So we can only declare locals at interior points. Absolute maximums and minimums, extrema, can occur anywhere on that spectrum. So what that means too is that you can have a local and an extreme or an absolute maximum or minimum at the same point. So I describe that a little bit down here where I say, hey, just note local extrema can only occur at interior points. So therefore, in this take, we have A and D. These points A and D could not have been local extrema, whereas absolute and min can occur anywhere. So technically, this point here could have been an absolute max. It just so happens that it's not the tallest one on the graph. So in the beginning here, you just need a little bit of practice really with distinguishing this. It's kind of hard to pick it up quickly when it's just a lot of talking. So what I'm going to do is I'm going to go to an example here and try to really show you the keys of what you need to do for this. Okay, so this example basically talks about finding all absolute and local extreme values. So that's going to be sort of the key concept that we're going on here. So we want all absolute and local extreme values. So what we need to do is we have very special values of x that are located here. We have A, B, C, D, and E. This is clearly marked as the interval A to B, okay, on the full spectrum. So we're only concerned about that specific interval of values. So we're going to go basically through and identify what those are. Now, me personally, it doesn't matter where you start. So let's just, for argument's sake, we'll start at absolute extreme values. So absolute extreme values can occur at any part of the graph at all. So on the entire interval. So all we're looking for is the lowest value of y, and you're not going to look very far. It looks like at x equals a, we have an absolute min value. Okay, so that means that it is the shortest value of y on the graph. So what about absolute maximum? Well, it appears that the absolute peak of the graph is up here. So we have an absolute max at an interior point at x is equal to e. All right. So there's no other absolute maxes. Now, worth noting, if we had another point, let's say this point here was also up here at the same exact value of y, we could have two absolute maximums, but only if they have the same value of y. Same thing works for minimums. Okay, moving on. So what about local extreme values? So local maximums can only occur at interior points, which means the only options for that are A, C, or C, D, and E. C, D, and E. So let's identify. Let's go to C first. So at this value here, it looks like it's the highest point within the vicinity of all the points around it. So we would call that a local max. Okay, if we go down to D, we would look at that and say, well, this appears to be the lowest point in the vicinity. So that is called a local min. And then if we go to E, this is an interior point, and it is the highest point within the vicinity that's there, which means not only is this an absolute max, but this is also a local max. So this guy here is both of them. So literally, this we will just say is no, let's say nothing, just for the sake of it. I know it's probably a poor word, but it's not neither local or absolute extrema at all, and that's possible. But this would be how you designate whether something is an extreme value by the two types that are there. Okay, if you look at the absolute and local mins and maxes that are labeled in this graph here, we can actually make some generalizations about them. So it says for, right here, it says for f of x, letters C and D, so let's highlight those. So letters C and D represents point where the derivative of the tangent line is going to be equal to what? Oh, look at that. Now we're getting to calculus. So if we were to draw a tangent line at this point or at this point, the derivative would be equal to what? Well, what would be the slope? It looks like it's a horizontal, perfect horizontal line, so the slope would be equal to 0, therefore the derivative would be equal to 0. So that is a profound, important concept. If you recall, we did do something like that in the last problem in one of the previous sections. Okay, let's look at letter E. Okay, so if we're looking at letter E, which is right here, so letter E represents, it says the letter E represents a point where the derivative what? Okay, this is interesting. So if we were to look at this closely up here, let's get rid of all the noise. So what does this look like to you up here? This does not look like a perfect, like, hey, it's flowing really nicely type point. It looks like it actually comes to here and then jags this way. What does that look like to you from a previous section? Hopefully that looks like a cusp to you. And if that's a cusp, but what do we know about the derivative at that point? It does not exist, right? So remember, it's not differentiable at a cusp, which means there is no derivative at that point. So a very interesting dynamic here has existed. If you look at all of the local extrema, they all occur when either the derivative is 0 or does not exist. Well, that is actually what the definition here is about. So all of these points are called critical points. Specifically, these points right here are called critical points. I call them, by the way, CPs because we do a lot of work with them, so we don't have to keep writing it out. They are called critical points, and they always occur wherever the derivative is 0 or the derivative fails to exist. So it all sort of came together there. Hopefully you understand the concept. So basically, when we're doing these problems, this is something that you want to keep track of in terms of understanding what you're doing, is that we're going to be identifying critical points a lot within the scope of what we do. Okay, so just summarizing what's going on here, right here. It says critical points therefore can be found if the derivative is either 0 or does not exist at any interior point. So on the domain. So more importantly, these points will always be possible max or min values or extrema. So we use critical points to identify where the max and min values are. Well, duh, look. Anytime we got a critical point, where did they exist? They existed at max and min values, which is a big deal for what we're doing. Okay, so now we have to come down to a big summary here on the most important concepts. It says, therefore, for almost every single problem you come across that requires locating extrema, in order to determine the critical points of the function, you must set the derivative equal to 0. Okay, so that is a big deal. We must set that derivative equal to 0 because the derivative is the slope of the tangent, and we want it to be the case. Now, it also occurs where the derivative does not exist, but that is very rare in the problems we do. Why? Because do you normally see cusps in or corners in typical functions that we manage? Not really. We're normally doing problems that are polynomials, things like that, so we don't have to worry about that type of stuff. We will talk about that more in a second, but that is an extremely important concept here. So the big takeaway is that we must set the derivative equal to 0 to find critical points. And now that you learned about how to identify local and absolute extreme, what we're going to do is we're going to move away from local extrema. We're going to leave that till the next section, and we're going to concentrate in this section solely on locating absolute maximum and minimum values. So that's going to be our focus as we move forward in just this section. So I give you a procedure here which is very useful for identifying this stuff. For example, number one, what do you do when you want to find absolute maximum values? The first thing you always do is you locate critical points. Well, how do you do that? By determining where the derivative is equal to 0 or does not exist. So what's next? We need to find all, you want to evaluate what the function value is at all the critical points and the endpoints. So what does that mean in a nutshell? We need to find all the values of y, right? That's when they say evaluate f, they mean basically sub in and find the values of y. And then all you have to do from there is find the largest and smallest values of y, and those are going to be our absolute max and min. So that's where we're going in terms of these problems, and that's what we're going to do when we're here. Now note again, the graphs are definitely not going to be given to you in any way. Why? Because you could just look at the graph and see it. Now, in an in-class setting, you would not have the graphing calculator. You're not allowed to use it. But of course, when you're at home, you'll have a little bit of the ability to be able to do that, which you normally don't do, to check your work, which is fine. It's just knowing how to do the absolute min and max, you'll be required to show that work as I do it right now. Okay, so number 2, we're trying to find the absolute maximum and minimum values of the function, the third degree function sitting here on the interval 0 to 4. So the plan is we have to follow the procedure here that we mentioned in order to determine what these are. So what was the first thing? Well, in these problems, we always identify the critical points by setting the derivative equal to 0. So the first thing we need to do is we need to find the derivative. So the derivative of this, hopefully by now, it should be absolutely fluent. You don't have to write out the ddx's and all that stuff. Also take note that we're back to the original derivative stuff. We're not doing, there's no implicit differentiation, and you won't see that in any other section from here on out. So we're going right back to taking ddx of the whole thing. So what are we going to get? We're going to get 3x squared minus 12x plus 9. Okay, so very interesting. This is the derivative. The whole goal is we need to set this equal to 0 in order to find the critical points. Like that. So all this is algebra, right? I told you before, you will be doing plenty of algebra, and here you go. So you wouldn't factor this as is. You're always going to, take that's not right. So you're always going to take out a GCF if you can, and if you do, you're going to get x squared minus 4x plus 3 is equal to 0, which means we can factor this into x minus 3, x minus 1. So that means if we set all quantities equal to 0, obviously setting 3 equal to 0 gets you nothing, but you're going to get x is equal to 3 and 1, and basically these are called critical values. Okay, why do they, sometimes they'll say critical points, but technically they're critical values because they're only values of x. So critical points are literally the coordinates on the graph that you get. So technically that's what we're trying to find. So in the beginning, we now know that the possible absolute max and mins occur at the following values. It says number 2, it says evaluate the function at the critical points and at the endpoints. So what do we have? We have 2 critical values, 3 and 1, and we have 2 values for the endpoints. So the best way to do this, believe it or not, is to make a simple f of x chart. Okay, so what do we want to do? We want to take our first value of x, which is here on our endpoint, then go to our first critical value, then our second critical value, and then where the graph ends. So I like to do it in order, so we literally can follow right through the graph and see where all these values are. So where are these located on the graph? Well, they're located at x equals 0, you're here. At x equals 1, we're here. At x equals 3, we're here. At x equals 4, we're here. So by doing this, we have identified essentially the 4 possible values that could be absolute extrema. Remember, absolute extrema can occur anywhere on the interval, where local, which is what we're not doing now, only can occur in the interior. So what do we need to do? Well, we need to this is really super simple. All we have to do is take each one of these values here, and we have to sub into the original equation. Okay, so this is very important. Do not sub these into the derivative equation. If you sub 1 and 3 in, you're going to get 0 because that's where the derivative is 0. And you're going to get other numbers at 0 and 4 that aren't going to do you any good. Remember, we're trying to find where the original function's highest values are, which means we need to plug these into there. So basically, what are we doing? For the first one, we're doing f of 0. So if we plug 0 into this, we get 0 minus 0 plus 0 plus 2, which is simply 2. If we do the same thing for 1, 3, and 4, we're going to get 6, 2, and 6. So basically, what do we have right now? So we have the coordinate 0, 2. We have the coordinate 1, 6. We have the coordinate 3, 2. And we have the coordinate 4, 6. So you might say, hey, I could have just looked at the graph. Again, you're not going to have the graph in most circumstances. So you need to be able to do this and show me the work without the graph, which means I need to see the work that you did and that you identified these points basically out of thin air, because that's what you're doing. There's no visual. You have to use the process in order to identify the points. So now, what do we have? We have essentially 2 critical points here and here, and then they're combined with the endpoint. So this is a CP, this is a CP, this is an EP, an endpoint, and this is an EP, right? So we have to look at these and say, of these, what are the absolute extrema? So usually I just do a summary statement. So you can say there's an absolute, and you can abbreviate, absolute max at x equals what and what. So what are the highest points on the graph and what x values are they located at? They appear to be at 1 and 4. So 1 and 4. So if they asked for just what values of x they're at, then you give them that. If they asked for the pure points, then you would actually include those. So the point 1 would be at 1, 6, and then this would be at 4, 6. So it just depends on what they ask for. Then we could do the absolute min at x is equal to, it looks like it's going to be 0 and 3. So we're going to get 0 and 3. So if they ask for the coordinates, you would write 0, 2, and you would write 3, 2. Okay, so essentially this is right here the answer to the problem. There's no number answer per se. It's more just telling the person that asked in the problem what are the absolute and extreme points or values, where do they occur. That's exactly what you're going to get. All right, so 3 more problems remain, all great examples. So let's start with 3. Absolute maximum minimum values for the 4th degree polynomial here on the interval -1 to 2. So we already have our endpoints of our interval here, which you can clearly see on the graph are located at -1 and 2. So just FYI, basically this here is kind of like not part of the graph here. So it's hard for me to eliminate that when I'm graphing it. So you can kind of, if you want to write omit or something like that, that's fine. But just realize it's only going from -1 to -2. Okay, so in order to find any extreme values, we have to find the derivative. So the derivative of this function quickly is going to be 4x cubed minus 6x squared. Okay, so note, you should be doing that just as quickly as I am. It's a very simple concept, simple way to do derivatives, just our basic derivatives. If you're not doing it that fast, then you need to study more because we're moving into an application section that's assuming that you're flying through basic derivatives. We have to set this equal to 0. So what you'll find is that I'm purposely choosing problems that bring back algebra concepts. Like this is a basic polynomial that you factor. This is a third degree, by the way, like a trinomial, not degree. It's a trinomial, not a third degree. But this is a binomial. So now how do you factor a binomial? Well, binomials are basically about GCFs. So it looks like we can actually take out a 2x squared out of this. So we're going to get 2x minus 3 is equal to 0. If we set both of these equal to 0, then we're going to get x is equal to 0 again, and x is equal to 3 halves. So basically, these are going to be our critical values for our problem. We'll call them CVs. They sometimes, like I said, sometimes people call them critical points anyway, but technically, since they're not coordinates, they're critical values. But we'll label that differently on the graph later when we do this. Okay, so once we have our critical values, we have now 4 possible values. We have -1, we have 2, we have 0, and we have 3 halves as the values we must test. So what do? We create basically an xy table, but we'll call it f of x. We start with our first endpoint, -1. We go to our next values in order, and then we go to our last value of 2, our last endpoint. All right, so what do? Again, we take all of these values and we sub into the original equation. Okay, so we are going to get some fractions here, but I'm just going to throw them in. So if we put -1 into that equation, we're going to get 3. If we put 0, we're going to get 0. 3 halves is going to be, I think it's -27/16, and 2 is also going to be 0. Okay, so once we have these, we basically have the coordinates on the graph. So we'll go over here and note again, this is also kind of omitted from the graph up here. And we can label the coordinates. So here we have -1, 3. So -1, 3 is an endpoint. We go to 0, 0, which is a critical point. We go to, it looks like 3 halves, -27/16, which is also going to be critical point. And then we go to 2, 0, which is going to be an endpoint. Any one of these values could be an absolute extreme value. We just have to find the highest and the lowest and summarize it in a nice brief statement at the bottom here. So we have an absolute maximum. It appears at x is equal to -1, and if we make that a point, that's -1, 3. It just depends on what they ask for in the problem. So just follow my math lab. I've seen in my math lab ask just for x equals, and I've seen them ask for the coordinate. So just be ready for either one when you do this. And then we have an absolute minimum. If we look at the graph, the maximum is the highest. The minimum appears to be down here. So that's going to be at x is equal to 3 halves. And the coordinate, of course, is going to be, as written there, 3 halves, -27/16 as our values. So basically, as I said before, this is the answer to your problem. And as you would give it to me on an exam or lab or any other situation you run into when you have to write it out. Okay, so in the first 2 problems, 2 and 3, we dealt with polynomials. So now let's go in the rational function world, okay, rational, and see how this process works for that. So if you look at the graph below, that is a kind of an abnormal rational function. You're more used to these types of rational functions, right? But this one's sort of a more less common one, but it is a legitimate rational function. So what do? Well, the process is exactly the same. We clearly have our n values here that we're going to use for our endpoints, right? So those are already there. We just have to find the other ones that are present in our picture. So we have, here and here are going to be there. So this is going to be sort of extra on this outside here. We're only going on that spectrum. So what do we have to do? We have to find our derivative, right? So right away, you should immediately look at this and go, uh-oh, this is a quotient. So if you're all of a sudden like going crazy galaxy braining here, and you tell me the derivative is 3 over 2x, please don't do that. I don't want to convulse. I want to keep my health. So make sure that you're back into the world of derivatives and you're showing this as a quotient rule. So remember, our quotient rule is going to be f prime g minus fg prime over g squared. So we just have to do that. So we're going to do the derivative of 3x times x squared plus 4 minus 3x times the derivative of x squared plus 4 all over x plus 4 squared. All right, so a lot of work to do here. So we can do a little shortcut work. This is going to be 3. This is going to be 2x. So moving on, it looks like we're going to get 3 times x squared plus 4 minus 3x times 2x over x squared plus 4 squared. Okay, now, here's the deal. While you could shortcut the process, and I used to say, hey, just box your answer, you're done, you can't do that anymore. So I gave you a break back then. You can't really do that here because I need the equation of the derivative in order to actually set it equal to 0. I can't set this garbage equal to 0. This will be a disaster. I need a one quantity, which means I must do the work. So here we go. What is the work? We're going to get 3x squared plus 12 minus 6x squared over x squared plus 4 squared. And finally, if we combine like terms, we're going to get negative 3x squared plus 12 over x squared plus 4 quantity squared. So this is the derivative of our function, which we now must set equal to 0. So if we do negative 3x squared plus 12 over x squared plus 4 squared is equal to 0, you might look at that in the beginning and go, oh my lord, like that's crazy business. Like what? I actually have to do that? Well, believe it or not, this is actually super simple. Why? Because what's the first step of a problem like this? I have to multiply both sides by the denominator to clear the fractions. But what happens on the right side? The entire denominator becomes completely unimportant. It becomes 0, which means all I have to do is solve this equation. I get negative 3x squared is equal to negative 12. I get x squared is equal to 4, and x is equal to, be careful, positive and negative 2. So what's the biggest mistake there? Putting just the positive 2, and look at what you would actually miss out on over here. If you just do the positive 2, you'd miss on an entire local minimum going on there, which we'll talk about later, but in terms of absolute, it's also going to be an absolute minimum. So what does that mean? So we now have our possible absolute extreme values at our critical values and our endpoints. So now, like we've been doing, we have to set this up in an xy chart. We'll say xf of x. So we start at negative 3, we got negative 2, we got 2, and then we got 3. So what do we need to do? Like we've been doing is we need to take these, we need to put them into our original equation up here, and we need to get at the points of importance here. So if we plug these in, we're going to get crazy fractions. So actually what I'm going to do here is I'm going to make this a little bit better and spaced out just because it's going to be fraction results. So negative 3, negative 2, 2, and 3. So if I put negative 3 in there, I actually get negative 9/13, which is approximately 0.69. Now, why am I doing an approximate value? Because I'm not going to have the graph, and do I know what 9/13 is off the top of my head in decimal form? No. I need to be able to compare that to the other fractions. So, for example, if you put negative 2 in there, you get, and reduce it, you get negative 3/4. Well, that is negative 0.75. This is a negative, by the way. And then if I plug 2 in, we're going to get positive 3/4, which is positive 0.75. And if we plug a 3 in, we're going to get positive 9/13, which of course is positive 0.69. So we need to compare these values, which one is the highest and the lowest. And you can clearly see that this guy here is going to be the lowest value, and this guy here is going to be the highest. So how would we summarize? We would say there's an absolute max at x is equal to positive 2, and if they ask for the coordinate, you're of course going to write 2, 3/4. And you would say that the absolute minimum is at x equals -2, because it's the lowest point on the graph, right? And that coordinate, if asked for, would be 2, -3/4. So basically, this would be your answer to the problem. Now, this entire time, you're running blind here. So in most scenarios, unless you have the graphing calculator, you're not seeing this. So you're relying on your calculus, algebras, and your everything else in order to basically do this blindfolded without a graph. So it's really easy to look down at the graph several times and go, oh yeah. But in reality, you're not going to have that. Now note, your absolute min is at -2, so I just noticed that. So this is a -2. So just be aware of that when you're doing the problems. This can be a little bit more challenging when you're not seeing the graphs. Okay, it would be poor of me to move on without doing a trig example. So if you look at the graph here, we have all radian values on the x-axis, and y values are the typical integers. So our interval is now going to be of radian values. So our endpoints are going to be decided by EPs, are going to be decided by, just a minute, I'm not going to write that anymore. Our endpoints are going to be decided by 0 to pi, are going to be where they are. So basically we're at here and here will be that deciding, so we're going to be ignoring this part of the graph. Alright, so in order to do a problem like this, same idea, we need to find the derivative. So the derivative of x plus 2 sine x is going to be 1 plus 2 cosine x. Okay, again, that should be lightning fast. You will also notice, as a side here, there has been no chain rule, product rule problems in here. I normally do not do that when it comes to some of these applications because I want you to get the absolute extreme concepts down. I don't need to be bringing in advanced derivatives in order to do that. So a lot of these you're going to find are going to be base functions. So here's our derivative. What do we need to do with that derivative? Where this is where things get a little bit funky. So I need to set this derivative equal to 0. So what this is if you remember, if you looked at the section 1.4 trig review video, if you want to go back to that, maybe that's a good thing to do right now, but that is where I talked about solving trig equations and how you will have to do that in this class, and here we go. So we subtract 1 to both sides, and then we divide by 2 to get cosine x is -1/2. So what do we need to do? We need to solve for the cosine x is -1/2 on the interval 0 to pi. Okay, so what are we doing? We have to go back to old school here, right? We have to go back to old school trig, and we have to take a peek at what's going on. So remember that the cosine is always the x coordinate on your unit circle, and if we have an x coordinate of 1/2, that occurs at values of pi over 3. Okay, that is something you should know. So but the key part of this is we are still dealing with this stuff. All students take calculus. So when we're doing this, we're looking for when the x coordinate is -1/2. So when is cosine negative? Cosine is negative in these two quadrants, which means that it is negative at 2 pi over 3 of the pi over 3 family and at 4 pi over 3. So if this was on the interval 0 to 2 pi, my solutions for x would have been both of these. But note, this is only on 0 to pi. Okay, this is just for this problem. So therefore, our only solution to our problem is 2 pi over 3, and this is our critical value for our problem. So what do? From here, we do the same thing we've been doing. We have to find our xf of x. Now, what's different about this? Every single other problem had 4 values of x. This one starts at 0, goes to 2 pi over 3, and ends at pi. Only 3 possible critical values or endpoints that we can actually use for the problem. So what do we need to do? So this is where more trig comes in. We need to take these values here, and again, we need to sub into the original equation. Do not sub it in here, or you're going to get results you don't want that have no meaning. You need to solve it into the first, or put it into the first equation. So I'm going to write this out because most of you can easily just plug in numbers, regular integers, and do it mentally. But with trig, it can be a little bit nasty. So I'm going to just put this over here. So what's f of 0? F of 0 is 0 plus 2 sine of 0. Well, both of these are sine of 0. Remember, if we're going real quick. So at a rotation of 0, we have a coordinate of 1, 0. Sine is the y, which is 0. So the whole thing is 0. So this is 0. F of 2 pi over 3 is going to be 2 pi over 3 plus 2 sine of 2 pi over 3. Okay, well, 2 pi over 3 is right here. The coordinate, remember, sine is positive in that quadrant, which means the sine of it's going to be the y coordinate of the coordinate root 1/2 comma root 3 over 2. So the y coordinate is going to be root 3 over 2. So this here is root 3 over 2. So what are we going to get? We're going to get 2 pi over 3 plus, it looks like 2 times root 3 over 2 is just root 3. And this approximates to about 3.83. So again, I'm going to write it. So 2 pi over 3 plus root 3, which is approximately 3.83. Okay, remember, we're evaluating this for how high and low on the graph is, so we need the decimal. Okay, so what about f of pi? So let's eliminate this here, and we'll throw it in over here. So what's f of pi? So f of pi is going to be pi plus 2 sine pi. Well, remember, pi rotation is here at -1, 0, but sine is the y coordinate. So this whole thing is 0 again, and we get just pi. So this is pi, which is approximately 3.14. Okay, we look at the whole ball game here, and this allows us to write our summary, which I'll write in blue. So the absolute max is at the highest point on the graph, which is at x equals 2 pi over 3, right? So if we were to write that in coordinate form, that would be 2 pi over 3, comma, 2 pi over 3 plus root 3. Okay, we tend to stay away from decimals. I'm not going to be so picky, but it's really good to write exact values. And then the absolute min is the lowest point on the graph, so you would go here and go, oh, it's at the lowest value is x equals 0, which is at 0, 0. If we look at our graph, we go, yep, at 0, 0, we have the absolute min. At pi, it looks like we're going to have the absolute max. So that would be the solution to the problem. So yes, you got to know your trig. That's the summary of the story for this.